So let's consider if we have two tensors, one tensor is T and the other is N, and these two alphabets I am putting to denote the order of the tensor. So it doesn't mean function. Maybe I should not write like this. So this is a tensor T, order is small t, which will be a whole number. N tensor, order is N, small n. Both are greater than or equal to. If you take a double dot product, it will result into a tensor of order t plus n minus 4. We denote this double dot product like this. We put two dots. We put two dots here. In general, t double dot n will not be the same as n double dot t. Okay. So I'm going to illustrate, explain how this double dot works, taking a specific example in which both the tensors are of order 2. Just a special case. I believe looking at what happens to this case, you will understand what will happen to other tensors of higher order also. I wanted to introduce this idea of a double dot product of two tensors, and I was saying that it is defined for two tensors where both tensors have orders greater than or equal to. This is the rule I am defining. I means the community, the scientific community defines the dot product like this. Okay. So following this rule, the first dot product will be between this and this. They will come together, dot with each other. Their identity will vanish in a manner of speaking. And then whoever is coming from the left, next one, whoever is coming from the right, next unit vector, they will be asked to dot with each other. Let's see what turns out to be. They participate in the dot product operation. The other dot is here, standby. Currently it is standby. What happens to these? What do I do with delta IQ? Throw it away and replace remaining I by Q. Are we okay? I replaced all remaining Q by I. Now they are facing each other. They must dot now. Threw away delta, replaced. What did I do? What did I do? Replace all P by J. Can't simplify any further. Two questions arise. First of all, what order tensor is this? It's a scalar. No unit vectors. Is it in line with what I anticipated? The resulting order of the resulting tensor, T plus n minus 4. In that case, T and both are 2. So 2 plus 2 minus 4, 0. That's what is expected from this rule, and that's what is happening. Again, you can visualize, as I was saying in the morning, one dot product sacrifices 2 unit vectors. 2 dot products, 4 unit vectors will be sacrificed. The other question, how many terms are here? This summation, how many terms are in this summation? In this summation, answer is 9. I hope everybody is clear about this. If not, then please ask. So what we are seeing that the number of terms in the summation following Einstein's notation has actually nothing to do with the order of the tensor. It has to do with something else. In this case, the double dot products. All right. So those two are two different things. Keep this in mind. All right. Transpose of a second order tensor. Now I'm talking only about a second order tensor. What is meant by transpose of a second order tensor? Suppose M is a given second order tensor. We know it is a second order tensor. We will denote the transpose of M, that is also a tensor, by M superscript T. Okay. And how is it defined? M transpose will be looks like M itself, but there is a difference. See the difference? What's the difference? Ij, here it is Ij, but here it is Ej here. That is the definition of transpose. So M, of course, M we would have written as Mij Eij. I'm not talking about any matrix here. Don't confuse this with matrix. Matrix is a way of expressing or writing the 9 components of the tensor. Very helpful in doing programming on a computer, very easy to implement. But it's not an integral part of the definition of tensor. It's not even a part of the way I express tensors in a Cartesian coordinate system. I don't need matrix right now. Okay. Based on this, what should be the condition? M transpose. That's the definition. Not generally true, true for some tensors. And in this case, it will follow that Mij will be Mji only when it is symmetric. This is the kind of thing we were talking about earlier when I was showing you dot product. Okay. Symmetric and anti-symmetric parts of a second order tensor. More definitions. Suppose A is a given second order tensor. I'm not saying it is symmetric. Any second order tensor. We can always split this tensor into two parts. One which I call A sim and another which I call A anti-sim. Okay. Where A sim is, actually it stands for symmetric. Why not write the full thing? Any tensor, second order tensor, can be split into a symmetric tensor and an anti-symmetric tensor. Yeah. Asymmetric part will be what? A plus A transpose by 2. It does turn out that this tensor, let's call it A sim, will be equal to A sim transpose. It does turn out. So the name is for a reason. This is a symmetric tensor. You can verify. The A anti-symmetric part is defined as minus, yes. Okay. Now this tensor, which is any tensor which is anti-symmetric, actually will have this property. Right? And when I is equal to j, what will happen? Turn out to be 0. You can verify. Okay. Later we will learn that the velocity field gives rise to a second order tensor. Velocity is a vector, but we will do something to the velocity field of a flow. It will become a tensor, and then the symmetric part will become the rotation rate, the rate at which a fluid element rotates. And the anti-symmetric part will become the rotation rate. The symmetric part will become strain rate. Physical meanings it will have. Right now it's mathematical, but I'm doing all this because I will encounter such physical quantities. Okay, this is the definition. All right, what next? Spatial derivatives of tensors. Spatial derivatives. Okay. We need to learn this also, again, because it will come in the equation. I define a new operator, which I call as, or we call as, the del operator. It is a vector operator. Okay. It is also called sometimes as the nabla operator. Some books will write that as the nabla operator. In Cartesian coordinate system, this operator, symbolically we will write it like this. Underbar. Underbar means that it behaves like a vector. You can say behaves like a tensor of first order. This is the definition in Cartesian coordinate system. Does it make sense? There is a unit vector E1, E2, E3, the basis unit vectors of my Cartesian coordinate system here. But then there is this partial derivatives. Partial with respect to x1, E1 plus partial with respect to x2, E2, E3. It is ready to act on something. On by itself, it doesn't have any number or quantity, but it can act on something. If I use index notation, I will write it like this. I hope you will accept it. Following index notation. Okay. Before I move further, I want to ask you, what do you understand by this? And the reason I am asking, because earlier when I have taught this course, there is a good number of students who are not clear what it actually means. In some maths course, you would have been taught by this time. This is partial derivative with respect to x1. What is x1? x1, x2, x3 are the coordinates of an arbitrary point referred to this coordinate system, Cartesian coordinate system. So what exactly del x1 is? I mean, going to the very basic calculus. What does this mean? After all, this is a symbol. By itself, it doesn't mean anything. We must have signed an agreement at some point. This means something. What does that mean? So let me, for us to understand this more easily or remind ourselves more easily, let me put del f del x1, where f is a function of many things, say x1, x2, x3. Let's put even time here, some function. And I have been given this quantity del f del x1. What is this? And what does the symbol mean actually? It means rate of change of f, right? Rate of change of f. But if I have to find f somewhere, minus f somewhere divided by delta x1, limiting value delta x1 going to 0. It means something like this. That's the rate of change, right? Basic calculus. My question to you is, what are these things here? What should I write? पहले ये करते हैं. What should be this? x1, x2, x3, t. This is the base value. First measurement you have made of this quantity, right? Now what should be the second measurement? x1 plus delta x1, x2, x3, and what happens to time? T only. All independent variables maintained at their original value. Only x1 is given the freedom to take an independent increment. When you measure the difference between f, divided by delta x1, take delta x1 the limit. That's what it means, del f del x1. Okay, good. Seems like you guys are well aware of this. First problem set, which I am going to upload today, will require this kind of understanding. to solve a couple of problems there. Okay. Let's come back to the del operator. What do I have here? Yes. So as far as the del operator is concerned, we will come across various ways in which this operator will act on a tensor, say T. All right. So here I am taking T to be a tensor of order T, small t. Big T is the tensor, small t represents the order. I have 4 columns here. First I will tell you what it is called, I mean in the community. It acts in a particular way, del. What it is called when it acts in that way. What is the symbol of that? Order of the resulting tensor, and is there any restriction on T? Right. First one is the gradient. It's called the gradient of tensor T. Okay. When you're talking about gradient of tensor T, you're doing this. Actually, it is more than a symbol. I should call it symbol or operation. In fact, yeah, take it, symbol or operation. Operation would be appropriate. Let me see. What are we? How it is acting actually? I said ways. This is the way it acts. Del T. So you may wonder, there is nothing between del and T. So what is it supposed to do? It may do something. We have already seen dyadic products, right? Two vectors came together, even though we wrote A, B right next to each other, but there was a rule. What was the rule? It is magnitude of A, magnitude of B, unit vector A, unit vector B. In the light of all that, it may after all do something to T. We will see. I'll take one example from each and illustrate that. The resulting thing will be a tensor. This whole thing will become a tensor. What will be the order of the resulting tensor? Any guess? I know I haven't explained it fully, but some of you may guess actually. अगर t का order small t है, tensor t, so what do you expect gradient will do to that? Same? Same? No, that's not correct. No, that's not correct. We'll increase it by 1. It will become more clear when I give the example. Is there any restriction on T, or we can talk about gradient of tensor of any order? The way it is defined, yes. It can even act on a scalar, and if it acts on a scalar, the gradient of a scalar is going to become a vector according to the what I have written here. A vector will become a second order tensor and so on. The second way in which it acts is called divergence of tensor T. What is the operation? Operation is this: dot product between the gradient operator and that tensor. Any guess what will be the order of the resulting tensor? T minus 2. Oh, you said 1, I thought. You are right actually. We are only talking in terms of T. What happens to T? You are right. T minus 1. You are right. Any restriction on T greater than or equal to 1? Because if it's 0, then scalar is there. You can't talk about dot product. All right. Third one, Laplacian. It's called the Laplacian of tensor T. Okay, Laplacian of tensor T. What is the operation? This is the operation. First two dels dot with each other, and then whatever is the resulting operator, that is going to act on T. Right? Symbolically, sometimes we write this as del square T, but mathematically it means this. Okay. Any guess? T. Very good. You have studied this in another class? Oh, okay. That's very nice. You are able to visualize. Any restriction on T? No restriction. Now, if you are not able to understand on what basis I am writing these things, don't worry. I haven't really explained, or I haven't really shown you. I was just asking because I know some of you will be able to visualize, but to ascertain these things, you are free to do right expressions using Cartesian coordinates, and then you will see these things are turning out to be true. Okay, so there is no magical step here, and you should not feel you are missing that magical step. If you're not able to understand, fine. Let's go to the next step. It will become clear. So let's work on this. So what I'm going to do, one example of each, and that will help you understand. Example of gradient of a tensor. For illustration, I am taking T to be a vector. In Cartesian coordinate system, I am asked to get the expression of that gradient of T in this coordinate system in the most simplified form. Okay, I start using index notation right away. Okay, nothing here, no dot, no cross, just standing like this. So now see what will happen. No dot here. I've applied what we call as the product rule of differentiation. After all, that's the product. Okay. Now at this point, let us assume something. The assumption is that the working coordinate system so far I didn't draw any coordinate system. I was only I didn't draw any reference frame. Now I am drawing a reference frame in the background. Something like this. Might have seen this in mechanics class. Reference frame F. Right? Reference frame, any rigid body, an observer fixed to that, and he observes various things. I am fixing my reference coordinate system to that reference frame. What is the consequence? What will happen to this? It will go to 0. Right? So when you change xm, basically what you are talking about something like, so let's talk about this del ep del x1. That will be one of these things. M takes value 1, 2, 3 after all. So let's focus on this. Currently, you are here x1 comma x2 comma x3. According to the definition of the partial derivative, this will mean what? Change in EP when the coordinates are changed from x1, x2, x3 to x1 plus delta x1, x2 and x3. That's what it means. Now, if this coordinate system is fixed in the frame, you keep choosing different locations, unit vectors are not going to change. They are fixed to the frame, right? And that is why, with this assumption, all expressions like this will be 0. Just feel like writing the whole thing here. Take any unit vector, take any coordinate 0. I will remove this, write all these 9 equations. Okay, so going back, I don't have to worry about this. Only worry about this. Okay, you can write it in a more familiar form where you put the unit vectors right next to each other. Even this means the same thing, but I have brought the unit vectors together. They start visually looking like a diagram. Index notation wise, is this okay? No index should appear more than 2 times. That's happening. How many terms inside it? 9 terms. Sum of 9 terms. What order tensor is it? Second order. Second order tensor because you have a dyad. Okay. Has it followed what I said? Acted on a vector and made it a second order tensor. What is mth component of this tensor? In this case, what is the mth component? Mth component. Del TP del XM or del XM del TP? Sorry, del TP del XM or del TM del XP? Del TP del XM. Keep this in mind. Later, this something that we get confused about. P ऊपर M नीचे, क्योंकि यहाँ ऐसे है और ये EM है. Now I'm talking about the mth component. Mth component, that order is controlled by this. Okay. Fine. Any questions? Is it clear? Now let's look at an example of divergence of a tensor. And in this case, I have taken the tensor T to be second order. It's just my choice. I mean, I could have illustrated it with something else also. And that choice is actually based on what we will see in the fluids equation later on. So let's work on this. Again, the agenda is to express this in Cartesian coordinate system of what I have seen, what I have shown, and in the least complicated manner or the most simplified form. Is it fine? Again, I could have applied the product rule of differentiation and written 2 more terms involving derivative of unit vectors, but by now we are agreeing that Now we are understanding that they are 0. So far I have used only Cartesian coordinate system to simplify all vectors and tensors. Suppose you have a different coordinate system. Some situations arise that you have to express a tensor in a non-Cartesian coordinate system. Do you know any non-Cartesian coordinate system? APL 100? Batao. Polar, cylindrical polar? One more you studied? Path coordinate system, right? Suppose the situation is that you are forced to express unit vectors in non-Cartesian, and then you are asked to find things like del dot t. Del is acting on various things. At that time, be extremely careful not to go from this step to this step, because some of the unit vectors there, they do change with space, right? So this omission of few steps I'm doing with awareness that the working coordinate system is a frame embedded Cartesian coordinate system. It should not become a blind habit. Do this for every coordinate system. Okay? Okay, so this part is straightforward. Now there is a dot product, but 3 unit vectors. Who all are going to participate in this? The nearest ones, right? EM and EP by rule. And what is the other unit vector going to do? Do nothing, stand by there at this operation. Is it correct? Okay. Same question. You may find it boring, but I'll keep asking because I believe that will give you practice. दो question पूछूंगा मैं यहाँ. Tala, what is the order of this tensor? First order. Is it in line with this? Started with 2 minus 1 1. The other question, how many terms in this summation? 9. 2 repeated indices P, Q. Let me ask you a question here. What is the jth component of del dot t in this case? What is the jth component? Okay. That's what you are saying? So P will be there, del P. Is that what you are saying? Right? Everybody with me? How I got the jth component? Extracted the coefficient of EJ, and EJ was not there. I repeated I implemented what I explained earlier in the morning. How many terms inside this? 3. Sum of 3 terms. And there is no unit vector in that sum. That is just this. Right? How many free indices in this? How many free indices? One free index. and that number of free indices in a scalar component is indicative of what? Order of tensor. One free index means first order. I was telling you in the morning, right? You either see this, the scalar component, and you can infer the order of the tensor of which this is one of the components, or you see the full expression of the tensor with the unit vectors, and you see how many unit vectors stand here. Based on that, you can infer what is the order of the tensor. So the moment you remove these unit vectors, it will have exactly that many free indices in the scalar part, which is the order of the tensor. If it is a second order tensor, you will take away EPEQ. There will be two free indices in the scalar part, right? In this case, you take unit vectors, but there is just one unit vector here. So this will be left with, it is bound to be left with only one free index. And that's why that one free index will also be indicative of the order of the tensor. Am I making sense? Next thing. Yeah, next. Laplacian. Example of a Laplacian of a tensor. T is a vector. I'm taking my choice. Let's illustrate. This is what the definition is. And in this definition, mind you, there is a parenthesis here. What is the significance of that? Significance is they should dot first, and then whatever is coming out from that, that is going to act on the operand or the density. Okay, so I'm going to write everything in this index notation, and first we have to simplify this part. That is going to be there is no dot here. There's no dot here. Just like that. TQ, EQ. Is it fine? Yes, sorry. Oh, अच्छा, ये मैंने एक्स्ट्रा लिख दिया. You are right. Thank you. इसके बाद आएगा. Is it fine now? And then this is going to become del square TQ del XM del XM EQ. Is a vector. How many terms inside it? Come on. 9. 9 Q. I'm only talking about the scalar component. Sum of 3 terms. And that will be del square PQ del x1 del x1. Q is a free index, indicative of the fact that it is the component of a vector, like before. And again, that becomes a free index the moment I snatch it away from this full expression and write it separately. वो free index बनना ही बनना है, क्योंकि वो उसका जो दूसरा वाला इंडेक्स था वो वेक्टर के साथ. All right. So those are the three things I showed on the slide here. Okay, this I have explained with examples. Now there is one more way in which the nabla operator or the del operator will come in front of us later, and that is through what is called the advection operator. Advection operator. The advection operator is defined in this manner: V dot del, where V is a vector. Okay. It can act on a tensor of any order greater than or equal to 0, and resulting tensor is also of the same order. Let's see quickly how it looks like. V dot del. How should I start? By this time I have shown many examples. I want to write it in Cartesian coordinate system in the most simple form. कैसे start करें? Vi Ej, Vi Ej, Vi Ei. That is the full V vector. Dot del vector. How do I write the del vector? Huh? And EM. EM is part of it. Okay. They will dot. So this is still an operator. Okay, it will still remain an operator, but will have a specific form. Vi del xm delta im. That is going to become Bm del xm. Still an operator. In its full form, it will be like this. Ready to act on something, whatever it is supposed to act on. Now let it act on itself. It will happen in fluid mechanics, where V will be the velocity vector and the advection operator will act on the velocity itself. What will this be? Can you simplify using index notation? V dot del, I already know what it is. I write it like this. What should come here? V. V should be written as what? VIEI. Any index except M is fine. VIEI. Again, frame fixed Cartesian coordinate system, no need to worry about derivatives. So what are we going to get? What order tensor? 1. 1. Which is same as the order of the tensor on which it acted. Acted on V order 1, resulting tensor is also of order 1. Of course, it's a different vector, but it is still a vector. Inside the whole thing, 9 terms. And if I snatch away, take away everything except the unit vector, I will get this, which has how many terms? 3 terms. And what would you call it if I ask you to make a sentence out of it? Yes, ith component of this vector.